All right. So, over the weekend, you should have looked at, finding area using one of our four approximation methods, right? Like RRAM, LRAM, MRAM, or trapezoid, and that would be just to approximate the area under the curve. Just using geometry that we know, like area of nice shapes. And if you haven't guessed, like chapter 4 is going to deal a lot with area. And so we wanted to find a symbol that represents finding area. We looked at approximation methods, over the weekend. This symbol means to find the exact area. And we're going to come back to that approximation method, during this first part of our chapter 4 as well. But I also wanted to give you some, definitions and some terminology here. So this idea of a definite integral. So when you see this symbol, right, here, right, that symbol right there, that's the definite integral symbol. Well, I should say it's an integral symbol. What makes it definite, right? What makes it definite is the fact that there are boundaries, A and B. And those boundaries mean you have a definite starting point and a definite ending point. And so the idea here is to find the area under the curve symbolically is represented by this symbol. So when you see that symbol, it's going to tell you find area. This function here, f of x, will either be given to you or as an equation or as in a graph. And then this extra, this extra dx here, right? That sort of goes with the integral symbol. They're saying, hey, like the function starts here with this symbol. The function starts right after you see this symbol and it ends after you see that symbol. So anything in between those two is almost like bookends. That's your function. Now, this dx, you should be a little suspicious, right? Because what do you think of when you think of dx? We just had a test on it, right? Differentials, derivatives. So somehow we're linking this dx here already at the beginning, but we won't see just yet. But this is the symbol that means to find area. Now, all these fun little, all these fun little arrows here, kind of telling you like the boundaries. This is your function. This is your curve. That's there. Sometimes I use the word curve, even if it's a straight line. Again, this is just your end point. This symbol right here represents find the area. So a lot of them, they're just going to be very basic geometry problems. Just getting used to that notation. So it says, okay, my function here is graph below, right? So this is the image of the function. If I read this, it tells me find the area under this curve. And I guess I should have said also under the curve up to the x-axis. So it's area under the curve up until the x-axis. I should write that too. Area under curve to the x-axis. That'll always be the boundary. I forgot to mention that, so it's good to rewrite that down. So now when I see this first part where it says find the area under f of x from 0 to 4, it's looking for this area right here. Right, it's finding that area. And yeah, we could use any number of approximation methods, or we could actually find the exact answer because it's linear, at least as the boundaries are linear. It's a triangle that has a base of 4 and a height of 4. So area is 1/2 4 times 4, which is equal to 8. So again, just wanting to know that this thing means find the area under the curve. Here's your curve, right? This is the lower bound, the left bound. This is the right bound from 0 to 4. And then remember your dx sort of acts as a bookend. And, I'm going to give you like lots of little teasers. This is like, it does have something to do with derivatives, just we're not going to see it yet. So, okay, 0 to 7 for part B. So again, starting at 0, now going to 4, 5, 6, 7. So now going out to here. So now we're adding, in addition to that area of 8, we're adding this triangle here. And that's a 1, 2, 3 triangle by 1, 2, 3, 4, 5, 6. So it's 3 times 6 is 18, half that's 9. So that would equal 8 plus 9, or 17. Okay, and again, that's all it's asking us to do. Find the area under this curve. Oops, sorry. So from 4 to 10, so then I'm looking from 4 to 10 here. So let me erase this. So from 4 to 10 is this triangle here. So that's a base of 6, a height of 6. 6 times 6 is 36. Half of 36 is 18. And then from just 2 to 6, so from 2 to, I believe 6 is here. So again, it's this triangle here plus this triangle here. And if you find that area just using geometry, this is an area of 4. And then this area right here would be an area of 9. So then 4 plus 9, which is equal to 13. Now, 0 to 4 of f of x plus 3. Like, think about like what's happening to this graph, plus 3. You're taking this image that you see and you're adding 3 to that image. So the x-axis is being pushed up 3 units. 1, 2, 3. So like here is where the new x-axis would be. And then you still have your graph. The image is still the same. So I'm still drawing this triangle, right? And then coming down, and then going up, and then coming down. So like if you just looked here, like that area just got pushed up, right? But there's still some more space under the curve. There's this entire space right here. So we've increased it a height of 3, but then to find its area, we just have to figure out, well, how far to the right are we going to go on our interval? So from 0 to 4, so you're looking from 0 to 4, which is a distance of 4. Remember, the entire graph got pushed up 3 units. So you've just added an area of 12 to whatever else the function was. And so this 3 is not an area of 3, but it's a height of 3 with a base of 4 because that was our interval. So, and then from 0 to 4, notice that was our first triangle up here, which had an area of 8. So this is 8 plus 3 times 4, which is 12, and 8 plus 12 is 20. Okay, similar idea, this minus 2 pulls everything down 2 units. So if I can find the area from 5 to 9, so 1, 2, 3, 4, 1, 2, 3, 4, 5 right here. So if I think about from 5 to 9, which is right here, so I find this area, this area here, and then I'm going to move the whole graph down 2 units. Well, I can kind of see like this part right here will eventually go away, right? Because if I move it down 2 units, that'll be below the x-axis, and I'll just be left with this triangular part. And we could see that in a similar way to get that arithmetically by finding this total area. So this total area would be 2 by 4, so that's an area of 8. 5, yeah. So it's this much right here is an area of 8. And this is a 4 by 1, 2, 3, 4. So it's a 4 by 4. 16 have that as 8 as well. So the whole thing is 16. From 5 to 9, this is 16. But we're going to subtract 2 times the distance from 5 to 9, 4. So we're going to get a total of 8. And again, it's because your graph, which looked like a house, right? So you find that area was 16, but then we're dropping that, we're taking away 2 units, but it's 2 units by a total of 4, right, from 5 to 9. So you're taking away 8 units. And so that your net change will be 8. Or you could think about it as like this part is going away, and so all that's left is just the triangular piece, which was just the top part. Okay, let's do example 2 as well. Again, this is just another graph. Geometrically, I can find it's a circle or a semicircle. So from -6 to +6. If I think about area of a whole circle, it would be 36 pi. That's only to the x-axis. That's half the circle. So that's 18 pi. And then if I just went from 0 to 6, right? Again, this is just this much of the area. From 0 to 6, that would be a fourth of 36 pi, which is 9 pi. Okay. Now, part C, we're adding 2. So again, thinking about this semicircle, got pushed up 2 units. So the 18 pi area still exists up here, right? But then we just added a height of 2, and that's a height of 2 by a span of 12 units, right? From -6 to 6. So that's an area of 24. So it's the 18 pi that we had plus 24 pi, plus 24 more. Not 24 pi, just a linear measurement, like a rectangle. Okay, now the last one on this example, that x minus 6, that's actually a shift to the right 6 units, not up or down. So since we're not shifting things up or down, we're not adding any more area under the curve. We're not subtracting any area from the curve. We're just taking the image and moving it to the right 6 units. So take this graph and move it to the right 6 units. So now it's from 0 to 12, which is perfect because those are our bounds, right? So we move it to the right, and now we're looking at that from 0 to 12. So we've just moved that area to the right, but it preserves its total area, so we still know it's 18 pi. Okay. So again, I'm hoping you just getting used to the symbol of this definite integral, which represents area under the curve, and it's all the way to the x-axis. There's not a whole lot of calculus that we just did. It's all geometry right now. We're just using one symbol, a calculus symbol, to represent area. And then we'll look at, in the next video, what happens if your area, or how could you make your area, or what does it mean to have area that has a negative value.